Okay, good morning. Welcome to Lecture 20, How Time Flies. So today we'll continue on statistical inferences or on inferential statistics, part 3. So in previous lectures, we talked about how to make or the general idea of making statistical inferences, right? So imagine this is a population. Um, and our goal is to you know, gain information about the properties of this population. But because a population usually consists of large amount of data sets or data points coming from many individuals, so the features of a population is typically very difficult to know. But then, it turns out that we don't have to um, study the population itself to understand the population. We can draw a sample from the population, right? Making sure, of course, the sample is as representative of the population as possible. And because the sample is usually consisting of less individuals, less data points than the population, the features of samples are usually easier to be known. So we can quite easily calculate the mean, the proportion, the standard deviation, right, of all the sample values. And so the purpose of um, inferential statistics, after we describe the sample, right, using all these descriptive statistics, is to make inferences about or to generalize all these descriptive statistics to the population so that we can have a fairly well guessed knowledge, so to speak, right, about the population. So this is like a two-way process, right? So first of all, we'll know something about the population. So to do that, we draw a sample from the population, and by studying the population, by studying the features of the population, we are able to generate some statistics that will summarize the features of the sample, and then we try to generalize these features back to the population. Okay, and so this process is to make statistical inferences. Okay, and we said that there are in general two kinds of inferential statistics, or two kinds of estimates, right? So first of all, we can have point estimate. So first of all, we can have point estimate, and then we can have interval estimate, right? Interval estimate. So some of you asked me, right? So they can fairly they can understand point estimate fairly well, right? Because this is a very straightforward idea. So we have a population, we draw a sample, and we calculate, for example, a sample mean or sample proportion. And then we use this sample mean or sample proportion to make a single guess about the mean of the population or about the population proportion, right? So that's the meaning of point estimation. So that's fairly straightforward. But then some of you asked, why, do we bother to supplement an interval estimation, right? That is, why do we bother to calculate any kind of interval after we have a point estimate? Well, this is a good question. So the reason that we usually supplement a point estimation with an interval estimation, um, because we would like to use this interval, right, to capture the uncertainty of making statistical inferences. So where do these uncertainties come from? Well, the uncertainty comes from we draw a random sample from the population, right? So imagine, right? Imagine we play God and we sort of know that the population means 4. And this 4 is obtained by calculating all data points from this population, right? But you can easily imagine that if we don't calculate every or include all data points from this population into the calculation, instead we'll only use a subset of the data points to do the calculation, then the mean that we calculate could be 4, but very likely it will be a little bit off from 4, right? It could be 3, it could be 5, it could be 3.7, it could even be 2, it could be even, could be any numbers, right? So, and if you draw one sample, you might get 3, and if you draw another sample, you might get a different number, a 4.1. If you draw a third sample, because a third sample will include a different subset of data points from the first two samples, so the mean of the third sample might be still different, right? Maybe, I don't know, 5.1. Okay, so these are the uncertainties, right? And these uncertainties arise from the process of randomly drawing samples from the population. So that means even though, for example, a point estimate of the population is good enough. For example, right, we just randomly choose one sample, right, and then we calculate the mean from the sample is 4.1. Then that's okay. So now we have a point estimate about the population mean, and this point estimate is 4.1. So this part is done. But as we just saw, right, there will be lots of uncertainties around making guesses from one sample. If you draw a different sample, you will likely have a different mean. So that means there are uncertainties about this point estimate. And to quantify these uncertainties, we use an interval, right? We're saying that, okay, so by a pre-specified confidence level, say 95%, right? We can calculate a certain interval from, let's say, 3.2 to 5.3. Okay, that means if I draw 100 samples, right? If I draw 100 samples, because I pre-specified that my confidence level is 95%, and I use the z-score associated with this 95% to calculate this interval, that will follow if I obtain 100 samples from the population. 95 samples will have their means be included or bounded by 3.2 and 5.3. Okay, so that's why this interval estimation is useful. Okay, so in other words, well, to just repeat, right, it captures the uncertainty, right, at a pre-specified confidence level. And of course, you can imagine if we want to be more confident, that is, we want to be 99% sure that our interval will include the population mean, we can increase the population level, and we should have actually a narrower confidence interval, right? If we want to be less confident, 80%, right? Oh, sorry. I should say that by choosing a higher interval confidence level, the interval should be wider, right? That way, we can be even more certain that this interval can include the population mean that we try to estimate. A lower confidence level actually means we'll have a narrower confidence interval, right? And of course, compared to this wider interval, right? By using a narrower interval, there will be more values that will fall beyond or outside of the interval. So we're less confident. Okay? Okay, so this is the idea or logic behind having confidence intervals. So yesterday we started to talk about how do we calculate, confidence intervals based on pre-specified confidence level, right? and we start by talking about sample proportion. So the idea is that we're trying to estimate a certain kind of proportion from a population. Let's say it's about a presidential race, right? We want to know how many people from the population, from our target population, will support a certain political candidate. And as usual, we would not be able to study every single body from this population, so we draw a sample, right, from the population, and we can calculate a sample proportion, right? Let's say 54% of people from this sample would support a certain political candidate. Okay, so this will be our point estimate. It's a single estimate of the population proportion. But as usual, right, we have to quantify the uncertainty about this point estimate, because by drawing different samples, the sample proportion might be very likely to change, right, because you're surveying different subsets of individuals. So to capture these uncertainties about this point estimate, we can calculate a confidence interval, right? And we said that depending on our goal and purposes, we can choose different confidence levels. We can choose, we only want to be 80% confident. We want to be 90% confident. We want to be 95% confident. We want to be 99% confident. So different confidence levels have different z-values associated with it. For example, right? So the z-value associated with 80% is, I can imagine, I don't know, it's about one something, 1 point something, I can't remember. But I do remember that the z-value associated with 95% confidence is 2, right? Approximately 2. And the z-value associated with 99% confidence is 3, right? So as you see, right, by pre-specifying the different levels of confidence, we are actually choosing different z-values. Well, why do we care about choosing different z-values? Because the formula to calculate the confidence interval is this, right? The confidence interval, CI, will be equal to the point estimate here is the sample proportion plus or minus the z-value at the pre-specified confidence level, right, times the standard deviation or standard error of the sample proportion, which is calculated by p sample proportion times 1 minus p divided by sample size, right, and sample size. So you see, by choosing different confidence levels, we'll essentially be supplying different z-values, right? So as we said, we typically use 95% confidence, this particular confidence level. So now we can sort of supply numbers, concrete values into this formula, right, to calculate the 95% confidence interval for this point estimation. So P we know now is 0.54, okay, and plus minus 2, right? The z value for 95% confidence is 2, so here's 2 times P is 0.54 times 1 minus 0.54, okay, divided by sample size. Let's say the sample size is 100, right, to make things easier. Or, yeah, okay, I think 100 will be good, right? And then we can start to use the calculator to calculate the confidence intervals, right? So, okay, let's do this together. So the first task, of course, is to calculate the standard error for sample proportion. So by using the calculator, right? So it will be 0.54 times 1 minus 0.54 will be 0.46. Okay, and then we use this term to this product term to be divided by 100. Okay, and then don't forget to take the square root of this you know, product term divided by 100. So that will become 0.54 plus minus 2 times, according to my calculation, this standard error is about 0.05, right? 0.049 something. So 0.0, 0.0498, 498. Okay, so that's about 0.05. Okay, so now we have this, and then we can start to calculate the confidence interval. So this expression simply means we first of all use 0.54 to plus 2 times 0.05, that's 0.10, right? So that will give us the upper bound, which is 0.64, okay? But then we also need to use 0.54 to minus 2 times 0.05. That will be 0.54 minus 0.1, right? So that will give us 0.44. So there we go. The confidence interval, 95% confidence interval for this, point estimation will be 0.44 to 0.64. That means if we draw 100 samples from this population, then for about 95 samples from these 100 samples that we draw, these samples will yield a sample proportion that's going to be larger than 0.44, smaller than 0.64, right? So that means 95 out of the 100 samples will produce a sample proportion that's bounded by this interval. Okay, and then we can also, based on this, confidence interval, to draw some conclusions. That is, uh, we can ask, okay, for example, given this confidence interval, uh, does this political candidate has the support from the majority of the population? Okay, does the majority of the population support this particular candidate? Okay, if we just look at this point estimate, we would tend to conclude that yes, this political candidate has the majority support because 54% is greater than 50%, which is an even split, right? But then this could be misleading because we know that there are uncertainties about these point estimates, and indeed by calculating, right, by calculating this confidence interval based on the sample size, the size of the sample based on the point estimation for the population proportion. We know that for the population, right, the support rate for this political candidate can go anywhere between 0.44 to 0.64, right? Of course, his or her support rate can be as high as 0.64, but it can also be as low as 0.44. And if it is his or her support rate is 0.44, then by no means this suggests that this political candidate has the majority support, right? In fact, if his or her support rate is 0.44 or any value that's below 0.50, which is included in this confidence interval, right? 0.50 is about here. 0.5. So exactly because 0.5 is included in this interval, that means the actual support rate can be higher than 50% or can be lower than 50%, as long as it's bounded by this interval, right? So for any value support rate that's, falling in this range, right, between 0.44 and 0.50, then we cannot claim that this candidate receives majority support, right? But if, let's say, right, for a certain sample and we calculate the confidence interval to be 0.52 to 0.63, right? I'm making a number up. Then, because this interval does not include zero point 0.5, which is the even split, right? Then we can conclude that this political candidate will have majority support because even though, right, his or her support rate will fluctuate, and will be as low as 0.52, that particular rate still is higher than 0.05, right? So that means even his support rate is as low as 0.52, still he or she has majority support. Okay, so that's how we can use confidence intervals to make some useful conclusions, and why confidence intervals are actually very important. Okay, so that's like a brief recap um, of the previous two lectures. I think it's worthwhile, right, to spend 20 some minutes on this topic because this topic is, I assume, quite new for most of you here. So it's worthwhile to repeat content so that it will sink in, I hope. Okay? All right, so yesterday we talked about, you know, the confidence intervals for sample proportions. Today we'll be talking about the confidence intervals for sample means. Okay, so today we'll be learning how to calculate 95% confidence interval for sample mean. So let's, specify some notations. Let sample mean be represented by M, sample standard deviation represented by SD, and sample size represented by N. Okay, um, should be should not be news here. And then we define, or the formula, right, for 95% confidence interval for sample mean will be this point estimate, right, sample mean, plus or minus the z-score associated with the 95% confidence level times the standard error for sample mean, right? We know this standard deviation. Turns out that standard error for sample mean will be standard deviation divided by the square root of sample size. Okay, so this actually is very much like the confidence, 95% confidence interval for sample proportions, right? Sample proportions times plus or minus the z-score associated with 95% confidence level times the ratio here, right? So the only difference is the standard errors are different, right? So this part is the same, right? The only difference is the numerator here, right? The numerator for the standard error for sample mean is its standard deviation, and this is actually the standard deviation for sample proportions. Okay, so it's very much the same. Okay, all right. Now we can look at an example, right? From a sample, for example, of 500 Honolulu citizens, the mean response on a 7-point scale on gun control is 4.2, right? On this particular scale, 4 representing neutral, doesn't have an opinion, and the standard deviation is 3. So we know that immediately we can draw some quick guesses. For example, we can perform a point estimate, right, using the sample mean, right? Because the mean response of this 500 sample is 4.2, so that means we can make a guess that the population mean, or the average population attitude toward gun control should be around 4.2. But of course, right, there will be uncertainties because if you draw a different sample of a sample of different 500 Honolulu citizens, you might get a different mean score, right? So there will be uncertainties, and we need to capture or quantify that uncertainty. And to do that, we can calculate the 95% confidence interval. Okay? we pretty much have everything here, every piece of information that we need, and let's figure this out together. So this is the question, and this is our formula, right? And then we can start to calculate the 95% confidence interval for sample mean. So here is what we know, right? The sample mean M is 4.2, SD is 3, sample size is 500, and the z-score associated with the 95% confidence level is 2. Now we have everything, okay? So now we can plug in the numbers and start to do the calculation. So 95% confidence interval will equal to 4.2, right? Plus or minus the z-score associated with 95% confidence interval. We know that's 2, and times SD is 3, right? Divided by the square root of sample size 500. Fairly straightforward, isn't it? Okay, so we have 4.2 plus minus 2 times we can actually, 2 times 3, that's 6. Okay, 6 divided by 500. Okay, so now you can start to use your calculators, right, to do the calculation. So it will be, let's say, okay, from my calculation, this part will be 4.2 plus or minus 0.27. Okay, so then we'll have the confidence interval. The lower bound will be 4.2 minus 0.27. Okay, so 4.2 minus 0.27, we have 3.93. Then what about 4.2 plus 0.27? That will be 4.47. Okay, so this should be our confidence, 95% confidence interval for this particular sample mean. Let's check the answers. Okay, close enough, right? So the standard error should be 0.13, right? That's close because 2 times 0.13 is 0.26, right? Well, because of rounding errors, right? I have here 0.27, that's close enough. And indeed, right, my answer here is very close to what I got, right, on the slides. So yeah, so the 95% confidence interval for this point estimate of sample mean is 3.94 to 4.46. Okay, so that means at 95% confidence level, right, the population mean can take any value from 3.94 to 4.47. We don't know an exact amount because we don't know an exact value because we don't study the population, but we have a fairly good guess, right? So if we draw 100 sample, right, then 95 out of 100 samples will have mean scores that's bounded by 3.94 to 4.46. Okay, so that's another way to understand the sentence. 95 out of the 100 samples that we draw from the population would have a mean that's bounded by 3.94 to 4.46. Okay? Okay, so now we can ask our question, right? So given this confidence interval, shall we conclude that, Honolulu citizens is in favor of or are opposing gun control? Okay? given this is the scale, right? So if we look at a point estimate, we might tend to conclude because 4.2 is larger than 4 is to the right of 4, right, in the direction of 7 in favor. So we tend to say, well, based on this point estimate, we want to say that Honolulu citizens should be in favor of gun control. But we said, right, before, this point estimate, useful as it is actually not uncertain, right? There will be uncertainties about this point estimate because if we draw a different sample, we'll have a different value, right? And by doing the calculation, we know that the fluctuation or certainty is bounded by this interval. That is, the average sort of attitude toward gun control can be as low as 3.93 and can be as high as 4.47, right? Then of course, if the value is above 4, then that means the population has an average attitude that's in favor of gun control. But critically, because the average attitude could also be as low as 3.93, which is below neutral point in the direction of opposition. So that means this population could also be against gun control, right? So in other words, because this 95% confidence interval includes the neutral point 4, right? So the sample mean or the point estimate of 4.2 is not meaningfully different from the neutral point and 95% confidence level. That is, in terms of absolute value, of course, 4.2 is different from 4. But statistically, right, the difference of zero point 0.2 can be as well be caused by random samples, right? If you draw a different sample, you could very well have a sample mean of 4 or 3.9 or 4.2, right? You don't know, right? So that's why we say, 4.2 statistically is not different from 4. So then we cannot draw the conclusion that average attitude toward gun control is in favor of the issue. Okay. Okay. So if we change the number by little bits, okay, to these numbers, what should be the 95% confidence interval? Okay. So you should probably do this by yourself. So you should pause right now before listening to my explanation. Okay? Alright, so imagine you have paused and you have worked out your answer. So let's check your answer together. So we know the confidence interval formula for 95% is sample mean plus minus the z-score associated with 95% confidence interval times the standard error, right? It will be SD divided by n, sample size, square root of sample size. So easy, we just plug in the numbers. So the confidence interval will be 4.2 plus or minus. We know z for 95% confidence level will be 2, right? Times, what is SD? SD is 1.5. What is n? N is 500, but don't forget to take the square root of it. So it will be 500. Okay, easy enough, right? Okay, so just do the calculation. What is it? Okay, so according to my calculation, the standard error is about 0.07. Okay, it's 0.067, but to round it up, it will be 0.07. So this equals 4.2 plus minus 2 times 0.07 is 0.14. Okay, so that means the lower bound of this interval will be 4.2 minus 0.14. Okay, so 4.2 minus 0.14, that will be 4.06. The upper bound will be 4.2 plus 0.14. Okay, so that will be 4.34. Okay, so there we go. This is our 95% confidence interval for this particular point estimate of sample mean or population mean. Okay, so now I can ask you, okay, given this confidence interval, can we say that the average opinion of this population is in favor of gun control? Right, so this is our scale, right? So 1 is oppose. 4, as we say, is neutral, right? It's neutral. And 7 is in favor of. Favor. Okay? So given this scale and given this confidence interval at 95%, can we say that at 95% the average opinion of the population favors gun control? Can we say that? Think about it. Well, yes, you can, right? Because true, there will be fluctuations, right, in the sample mean as we draw different samples from the population. But despite the fluctuation, right, the sample mean can be as low as 4.06, which is still greater than 4, right, which is the neutral point. That means, sure, it can be very low as 4.06, but still is in the direction of favoring gun control. That's why we can conclude, right, that a 95% confidence level, the average opinion of this population favors gun control. Okay? So now we can have a rule of thumb, right? So if 95% confidence interval for a sample proportion or sample mean or any kind of statistics, right, does not include the reference value. It could be 50%, which is, the point that separates, majority from minority, right? Or the neutral point, or 0 point, whatever, right? So if this interval does not include the reference value, then we'll conclude, right? So that a sample proportion, mean, any statistic, does not conclude, right? So if the interval does not include the reference value, then our sample estimate will be meaningfully different from the reference value at 95% level. Okay. That means the difference is real, right? It's not by chance. It's not because of the sampling procedure. In contrast, right, if the 95% confidence level interval for sample proportion mean or any statistics includes the reference value, right, 0, the neutral point at a attitude scale, or 50%, right, then the sample proportion, mean correlation, mean differences, the point estimate does not differ, typo here, does not differ from the reference value at 95% level. Okay, that means the difference, right? Of course, for example, 4.2 is, in terms of value, right, different from 4, or the proportion of 52% is by value different from 50%. But because, right, at the statistical level, the interval includes the reference value, so we conclude that our point estimate, a sample proportion, a sample mean, is not statistically or not meaningfully different from the reference value, right? The difference is by chance, right? It's not real. Okay? All right, so that is pretty much about the confidence interval, right? The part on confidence interval. So, as I said, this is a rather new idea, I assume. The bottom line, I should say, is you should know how to calculate confidence 95% confidence intervals for sample proportion and sample mean. And you should be able to draw conclusions such as, is the majority of the population in favor of the issue? Is the majority of the population prefer a particular candidate, or is the population average opinion favors the issue, right? As long as you are capable of drawing that conclusion based on the confidence intervals, which you know how to calculate, you should be fine. Okay? All right, so that's quite a bit of content. And practice and ask questions if you're still not understanding it. Make sure, right, you know how to do this by yourself. So this will be the last lecture for this week. And for next week, we'll probably have two more classes. That is, the content of this class will end on Tuesday. And then you will have Wednesday and Thursday to complete the last homework assignment and to review, to study for the final examination, which will be on Friday. Okay? All right, so let me know if you have any questions and have a good weekend.